Thank you for watching my videos all these years and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the question paper CSIR National Eligibility Test held in the month of December 2023. This question is from the section Complex Analysis and it is related to entire functions. This question is placed in part C, which is a multiple select question. There can be more than one answer and it carries 4.75 marks. The question ID is 704079. This question is also suitable for all these examinations. Right. The given question is, let capital X be an uncountable subset of the C, the set of complex numbers or the complex plane, and let F be an entire function from C to C. F is a function from C to C, be an entire function. Assume that for every z belongs to X, there exists an integer n greater than or equal to 1 such that the nth derivative of z is equal to 0. Fn of z, where Fn is the nth derivative of f. So, we assume that for every z belongs to X, there exists an integer n greater than or equal to 1 such that f, the nth derivative of z, is equal to 0. Which of the following statements are necessarily true? We are given 4 options. Option 1, f is 0, is a 0 function. Option 2, f is a constant function. Option 3, there exists a compact subset K of C such that f inverse of capital K is not compact. Option 4, f is a polynomial. Right. We will discuss the solution of the problem by taking the options one by one. We have f, C to C, an entire function. We are given capital X is an uncountable subset of C. Given there exists an integer n greater than or equal to 1 such that the nth derivative of f of z is 0 for all z belongs to X. That is the common hypothesis what we have. We go for option 4. Is f a polynomial? Right. We believe that it is a polynomial, therefore we will provide a proof for that. F of z is an entire function. It is known all the derivatives of f of z exist and each derivative is an entire function. Since f of z is an entire function, all the derivatives f, all the derivative, kth derivative, k belongs to n, of f exists and they are all entire functions. So, given there exists an integer n greater than or equal to 1 such that the nth derivative of f of z is equal to 0 for all z belongs to X. So, because f is an entire function, its nth derivative is also an entire function. Right. This implies f nth derivative of z is equal to 0 for all z belongs to x means each z belongs to x is a 0 of the nth derivative of f. So this implies x is the set of zeros of the entire function f nth derivative. The nth derivative of f. That is the function now. Right. Now, what is x? X is an uncountable subset of C. Therefore, it has a limit point in C. We require the existence of one limit point that is sufficient for us. But in fact, whenever x is an uncountable subset of C, then it has an uncountable number of limit points. But what we require is one limit point is sufficient. Using the Bolzano-Weierstrass theorem, uncountable means an infinite subset. Therefore, it has a limit point in C. Right. Now let us recall a famous theorem, that is the identity theorem or uniqueness theorem. Suppose that f is analytic in a domain, the connected domain D, if capital S is a set of zeros of f in D and has a limit point z star in D, then f of z is identically equal to 0 in D. That is, f is a 0 function. So here the nth derivative of f plays the role of f, and the entire complex plane plays the role of D, and capital X, the set of zeros of the nth derivative, plays the role of S, and x has a limit point in C, that is in D. Therefore, the nth derivative f of nth derivative of z is identically equal to 0 in D. So therefore, by identity theorem or uniqueness theorem, the nth derivative of f of z is identically equal to 0 in C. Right? So that is the one. That means the nth derivative of f is the 0 function. So that means the nth derivative f of n z is equal to 0. Integrating once, right? Integrating once, you will get a naught. Integral of the nth derivative is the n minus 1th derivative of z is equal to a naught. Now, again integrating, you will get a naught z plus a1. After integration, you will get f n minus 2th derivative of z is a naught z plus a1. Integrating again, you will get a naught, integral of z is z square by 2 factorial plus a1z plus a2. That is, this is the n minus 3 derivative of z. That is a naught z square by 2 factorial plus a1z plus a2 plus so on so on. Continuing in this way, after n steps, you will get f of z is equal to a naught into z to the power of n minus 1 by n minus 1 factorial plus a1 into z to the power of n minus 2 by n minus 2 factorial plus so on and so forth plus a n minus 1, which is a polynomial of degree n minus 1. So the nth derivative of f z is identically equal to 0 in C will imply f of z is a polynomial of degree n minus 1 by integrating successively n times. We have shown you in the snippet there. Agreed. So thus f of z is a polynomial. That's the conclusion of the option 4. So f is a polynomial. So option 4 is true. We move on to the next slide for the discussion of the remaining 3 options. Yes, that is the common hypothesis what we have. And these are the 3 options to be discussed. So for options 1, 2, 3, consider f of z is equal to z, the identity function, and capital X is the C, which is an uncountable set. F of z is an entire function, obviously. An entire function because it's a polynomial of degree 1. And x is equal to C is uncountable because C is uncountable. And f of z is equal to z, differentiating 2 times, you will get f to the second derivative of f of z is 0 for all z belongs to x. X is equal to C. Thus, there exists an integer n is equal to such that the second derivative of f of z is equal to 0 for all z belongs to x. So that means this function f of z is equal to z satisfies all the conditions of the hypothesis. But f of z is equal to z is not a zero function. F of z is equal to z is not a constant function. But f is not 0 and f is not a constant function. Therefore, options 1 and 2 are not true. So what about the third option? For any compact subset K of C, that is from the codomain we are talking about, we have f inverse K. Yeah, f inverse exists because it's both 1, 1 and 2, so on and so forth. F inverse of K. What is f? Identity function. I inverse of K is I inverse is I of K is K. K is compact. Yes, K is compact, coming out to be compact. But here in option 3, it is given not compact. Therefore, option 3 is not true. So for this particular example, for this particular situation, these 3 options are not true. Therefore, they are not necessarily true. Now, summarizing all the options, the answer to this question is option 4. That is the detailed discussion of the solution of this problem. For me, it is an interesting question, and it's also reasonably, it will take time to think it over to get the proof of the option 1. Option 4, right? Option 4 we have shown at the beginning itself. So getting this answer that f is a polynomial is little difficult, but otherwise it is an easy question. Right? I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We hope to meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.